Hi everyone, here is the part 4 of our reaction kinetics. So here we're going to learn about the reaction half-life. So what is half-life? So basically a half-life we give T half for a reaction is the time taken for the concentration of a reactant to drop to half of its initial value. Okay, so for a first order reaction, T half does not depend on the starting concentration. That is because when you find out the T half, it would give us the equation ln2 over K. ln2 is 0.693 over K. Now you may be wondering, how do we get this equation? The way we get that equation is, if you refer to a first order reaction, let me take you back to where we had seen the first order rate equations. Okay, so for a first order reaction, you see here integrated rate law, ln A naught over AT equals KT. So from this reaction, we can derive the T half expression for a T half. Now A naught is the initial concentration and AT is the time concentration at a certain time. Now T half meaning what is the concentration exactly after when the initial concentration become half. So instead of A naught at a certain time, what now we have is half of A naught. So with that in mind, we can calculate what would be the T half going to be. So if I show you the calculation here, let me show you it here. So we have ln A naught. So A naught is the initial concentration, and at a certain time, if the concentration is going to be half, instead of AT we can say it is A naught over half, right? Now AT is going to be half the concentration of initial concentration. That happens at T half, right? So ln A naught over A naught over 2. So A naught can get cancelled. So the 2 in your denominator will become now numerator. That this whole part will become ln 2. So ln 2 equals KT half. So the T half therefore is ln 2 over K. Okay, T half for a first order reaction. That is how we get that value. And similarly, while we are here, I'm going to let you know. So we're going to use this equation for the second order reaction to derive the T half. So remember that. And for the zero order reaction, we use this equation, integrated rate law, to figure out what would be the T half going to be. Okay. So with that in mind, okay. So here T half equals ln 2 over K, and now you saw how we get this expression. ln 2, if you put ln and then the number 2 in your calculator, it will become 0.693. So for a T half, meaning the time it takes for the initial concentration to become half is a constant, 0.693 over K. K is the rate constant. Okay, and it does not depend on the starting concentration. No matter what is the starting concentration, if you know the rate constant, you can find out the T half. So the half-life for a first order reaction is a constant. One example for first order reaction is a radioactive decay. It's a first order process. The half-life for a radioactive nucleus is a useful indicator for its stability. Now this graph explains you what is half-life and how the concentration going to be halved after each half-life. Now this is a plot of dinitrogen pentoxide versus time for 3 reaction half-lives. Let's say you started with concentration 0.06. What's the half of 0.06? 0.3. So 0.03. Exactly, this concentration will become half, and then we call that time as the T half. Now 0.3, if you take 0.03, half of that would be 0.15. So now 0.03 become 0.1015 exactly at another t half. If it is 24 minutes, in another 24 minutes time, this 0.03 concentration will become 0.015. And half of 0.015 would be 0.075. So this would become that concentration after another 24 minutes, t half. So after 3 half times, it would become 1/8 of the initial concentration. So this is 1 half, and then here you have another half. So after one half life, concentration will become half. After 2 half lives, one time half into half, 1/4. It would become 1/4 of the initial concentration. After the third half life, another half, it would become 1/8 of the initial concentration. Okay, so this is a graphical showing of how the half-life works and what it means. Okay. Okay, let's look at this example. Cyclopropane is a smaller cyclic hydrocarbon. Okay, because it has a 60-degree bond angle and it has a strain. So you would like to decompose. When you heat it up, it will become open chain and an alkene. Okay. And the rate constant for this reaction is 9.2 per second. And it says it is decomposing, or it will become rearranged, and it's a first order reaction. It's asking what is the half-life of the reaction. Remember, for the T half, for the first order reaction, T half is ln2 over K. Remember? And ln2 is 0.693. And then the rate constant is given 9.2 per second. So the T half would be 0.693 over 9.2 per second. That is the half-life of the reaction. That's easy, correct? And then it says, how long does it take for the concentration of cyclopropane to reach 1/4 of the initial value? Right? So the 1/4. Remember, we know the half-life, T half. When you do this calculation, 0.693 over 9.2 will give you the answer. Yes, over here, 0.693 over 9.2, 0.075. That is the T half. So it will become a quarter after 2 half lives. Remember, we saw in the graph, it would become 1/8 after 3 half lives. So to become 1/4, so you just have to multiply this by 2. So in 2 half lives, it would become 1/4 or 1/4. So 2 times 0.075, 0.15 seconds. Okay, pretty easy and straightforward. Now, for a first order reaction, T half does not depend on the initial concentration. Right? We saw that because T half equals ln2 over K, there is no concentration term. Now, for a second order reaction, T half is inversely proportional to the initial concentration. T half is going to be 1 over Ka naught. Now, we can also derive this equation from the second order integrated rate law. Remember, I will show this. I'll show it to you here. For the second order integrated rate law is 1 over AT. You can go back to the slide and see this for yourself. 1 over AT minus 1 over A naught equals KT, and this is the integrated rate law for a second order process. Now we are going to rearrange this for a half-life. Now if in the half-life at T half, concentration now going to be half of initial concentration. AT would be half of initial concentration, A naught over 2 minus 1 over A naught equals KT. So 1 over A naught minus 1 over A naught over 2 minus 1 over A naught. So 2 goes to the top and 2 over A naught. Okay, that would be 2 minus 1, 1 over A naught. From this side it would be 1 over A naught equals KT half. So T half then would be 1 over KA naught. Look at my A. 1 over KA naught. Right? So we just derived that together. 1 T half 1 over KA naught. And that is the same equation, T half, for a second order process. Okay? And similarly, you can do for a zero order reaction, T half is directly proportional to the initial concentration. So I'm going to go ahead and erase these things. So I can show you for the zero order one. For the zero order one, now this for this one, integrated rate law is AT minus A naught equals minus KT. And AT we can write, now it's going to be half of initial concentration minus A naught equals minus KT half. So half of A naught minus A naught, 1 minus half, right? Negative half A naught equals negative KT half. These two negatives cancels. So then the T half would be A naught over 2K. T half equals this amount. A naught over 2K. A naught over 2K. That's how you get the half-life for a zero order reaction. Okay. It equals K. That's how these expressions had been derived. We work on this one and we also work on this one now. Okay. I just wanted to show you how these expressions had come out. Okay. Okay. And this is an overview of zero order, first order and simple second order reactions. And for a zero order reaction, rate law is rate equals just the K, because if it is a zero order, you don't have any value here or a concentration term. First order rate is Ka, second order Ka raised to the power 2, second order. And these are the units for K. And then the half-life expression. Zero order A naught over 2K, first order ln 2 over K, second order 1 over Ka naught. And these are the integrated rate law in straight line form. Okay. And this is the plot for straight line. How do you plot it? Concentration of A versus time. Ln concentration of A versus time. 1 over AT versus time. And then what is the slope and the intercept? And then how does the graph look? Okay, this is like a summary of the three laws that we had learned. Okay. So now let's talk a little bit about collision theory and concentration. The basic principle of collision theory is that particles must collide in order to react. Right? If they don't collide, then there are no reaction. So how can we increase the collision? Increase in the concentration of a reactant leads to a larger number of collisions, hence increasing reaction rate. So we can increase the concentration. The number of collisions depend on the product of the numbers of reactant particles, not their sum. Number of collisions depend on the product of the number of reactant particles. For example, let's say you have two reactant particles, A plus B, giving you a product, let's say any product, right? So the number of collisions depend on the product of the numbers. Product means A times B, not A plus B. So this is the number of particles, however number of particles. I'll show you this in the next diagram. Okay, number of collisions depend on the product of the numbers of reactant particles, not their sum. Concentrations are multiplied in the rate law, not added. Remember the rate law, we write rate equals K A B. So the concentrations, they are products, so it's a multiplication. That's what product means. Okay, like the multiplied. Not, we are not adding A plus B in the rate law. Okay, like this. The number of possible collisions is the product, not the sum of reactant concentrations. So here we have two A's and two B's. So the way that they can collide is there are four ways. A, B, this A and this B, this A and this B, and like that. And you add another one, A. So there are 5 particles but total 6 collisions. And there are 6 particles but there are 9 collisions. So it's going to be the product of their particles. 2 times, yes. So this is 4 collisions, this one is 6 collisions, and there are 9 collisions. 2 times 2, 4, 2 times 3, 6, 3 times 3, 9. Not 2 plus 2, 4, 2 plus 3, 5, 3 plus 3, 6. So it's a product of the particles. Now, so far we have done our reactions at a constant temperature. So then the rate constant remains constant. Now what happened to the rate constant when you change the temperature? So temperature and the rate constant. Temperature has a dramatic effect on reaction rate. For many reactions, increase of 10 degrees Celsius will double or triple the rate. Experimental data shows that the K rate constant increases exponentially as temperature increases. This is expressed in the Arrhenius equation. So the Arrhenius equation is K is the rate constant equals, here A is the frequency factor and K is the rate constant. EA is the activation energy. There should be a negative over here. Exponent of activation energy over RT. Here R is the gas constant and T is the temperature. Higher the T, meaning higher the temperature, larger K, larger rate constant, and we have an increased rate. So the activation energy that we saw in our previous slide, in order to be effective, collisions between particles must exceed a certain energy threshold. Sometimes particles can collide with each other, but if they have not overcome the energy threshold, there wouldn't be any effective collision. So when particles collide effectively, they reach an activated state. The energy difference between the reactants and the activated state is the activation energy for a reaction. Okay, lower the activation energy, the faster the reaction. If you can reach activation energy sooner, meaning having a low activation energy, you will have a faster reaction. But if you have a high activation energy, so then it need more time sometimes. So maybe you have to increase the temperature to reach the activation energy. So smaller activation energy, meaning it has a larger frequency factor, which increase the rate constant, which leads to a increased rate. Now this is an example of a activated complex. You see here this athlete, so it has to reach to the level bar, and then he is reaching to the activation energy, to the activated complex over the bar, and then come back to the ground state. So similarly, collisions must occur with sufficient energy to reach an activated state. So there is a reactant and we have to give energy to come to the activated state. Once activated state is overcome, so the reverse reaction, so you will come to the products. So your products, if you have the products lower energy compared to the reactant, we say that is a exothermic reaction. So this particular reaction reversible but is exothermic in the forward direction, and it would be endothermic in the backward reaction. So increase in temperature causes increase in the kinetic energy of the particles. This leads to more frequent collisions and reaction rate increases. So when you increase the temperature, we can see a reaction goes faster. At a higher temperature, the fraction of collisions with sufficient energy equal to or greater than activation energy increases. So the reaction rate therefore increase. Calculating activation energy. So we can calculate the activation energy from the Arrhenius equation. And this is the Arrhenius equation. K equals A E negative EA over RT. So if you put this into the straight line form, you take the ln of both sides. Ln K equals ln A minus EA over R 1 over T. So this is a straight line form. Y equals mx minus c. Okay. Excuse me. If data is available at two different temperatures, let's say we have a rate constant for two different temperatures, we can also do this equation to find out at two different rate constants and two different temperatures. ln K2 over K1 equals negative EA over R 1 over T2 minus 1 over T1. So this is going to be the equation for that. If you have two different temperatures, T1 and T2, K2 and K1. Okay. Now this is a graphical form, the straight line. So ln K equals ln A minus EA over R 1 over T. So this ln K is the y-axis. Ln K versus 1 over T. Y equals mx ln A EA over R. 1 over T going to be your x-axis 1 over T. And this is going to be C. This is worded differently. C. Ln A going to be your intercept 1 over T. Okay. This is C, negative mx. Negative slope, y equals mx plus c. But this came to be negative form. It's okay. So you do a plot using ln K going to be your ln K going to be your y-axis, and your ln A going to be your intercept, and 1 over T going to be your x-axis. And then the slope would be EA. This is the slope. Okay. Graphical determination of the activation energy. From a graph also we can find out, once you draw a graph of ln K versus 1 over T, from the slope you can find out the activation energy, because R is going to be your gas constant. And if you have two different not activation energies, two different rate constant and time, we can find out the activation energy. Let's look at this one. The decomposition of hydrogen iodide, 2HI, giving you hydrogen gas and iodine, has rate constant 9.51 into 10 to the negative 9. At 500 Kelvin, 1.1 into 10 to the negative 5 at 600 Kelvin. We can find the activation energy. And R is given 8.314. We are given the rate constants K1 and K2 at two different temperatures. So we can solve for EA. So we're going to use this equation. You see here ln K2 over K1, EA over R, 1 over T2 minus 1 over T1 to solve this problem. Yes. So this is what we're going to be using. Negative EA 1 over T1 minus 1 over T2 minus 1 over T1. Okay, so if you plug the information given to us in this one, ln K2 1.10 into 10 to the negative 5 over 9.51 into 10 to the negative 9 equals, we don't know activation energy, and 8.314 is the gas constant, and 1 over T2 is 600 and 1 over T1 is 500. So first you do ln 1.10 into 10 to the negative 5, and then also you find ln 9.51. That would give you 1156. Let me do the calculation quickly. Use my calculator. And then you guys do the calculation too while I'm doing it. ln 1156. Okay, good. So from this side you will get ln 1156. So ln 1156 would be 7.05. Okay, from this side. And from the other side, when you get this part, you will get something like negative 0.33 into 10 to the negative 3, I believe. Okay, and then you divide this number by 8.314. So from this side you will have, so there are two negatives, this negative will get cancelled. From that side, when you divide 8.314, no, when you divide 0.33 into 10 to the negative 3 over 8.314, that would be 4 into 10 to the negative 5. Activation energy times 4 into 10 to the negative 5. So the activation energy would be that divide by 4 into 10 to the negative 5. That will give you the answer 7.05 over 4 10 to the negative 5. Why my calculator is not working with me? Okay, I was typing a wrong number. Yes, so that will give you a big number like 176250, which is 1.76 into 10 to 1, 2, 3, 4, 5. 10 to the 5 activation energy. Okay, that would be the activation energy. You also try to do the calculation and see if you're going to get the same answer like me. Okay, we'll conclude the session here.